We are discussing the second chapter, Calculus of Scalar Fields. Right now, we shall start the third module, Vector Derivatives. We start with the learning objectives. After studying the module, we shall be able to know what do we mean by vector derivative and directional derivative, why partial derivative can be considered as a special case of vector derivative, and finally, what are higher order vector derivatives. Let A y are two elements in Rn where y is different from 0. We define a set which we shall denote by Ly. It is the collection of all the points a plus t y where t is any real number. Since a and y are members of Rn, clearly Ly is a subset of Rn. We note that any element in Rn can be geometrically viewed as a point as well as a vector. Now, we claim that Ly denotes the straight line passing through the point A and parallel to the vector y. Let Z be arbitrary member of Ly. By definition, there exists a real number t such that we can express Z equal to a plus t y. In particular, if t happens to be 0, we have Z equal to a, that is, a is a member of Ly. If t is non-zero, then we have Z minus a equal to t y. This shows that the line containing the points Z and a is parallel to the vector y. This proves our claim. Now, we define what do we mean by a convex set in Rn. A non-empty set A subset of Rn is said to be convex if and only if whenever it contains two distinct points A and B, it also contains the line segment joining A and B. That is, whenever A and B are in A, for every t lying in the closed interval 0 1, we must have the points T A plus 1 minus T B in A. Now, we show that any open sphere SAR is a convex set in Rn. We recall by the symbol SAR, we mean the open sphere in Rn whose center is at A and radius is a positive real R. Let x, y be two distinct members in SAR. In order to prove that SAR is convex, we are to prove that the line segment joining x and y is also in SAR. Since x and y are members of this open sphere, we must have norm of x minus a as well as norm of y minus a both less than R. Now, let Z be any point on the line segment joining x and y. Then there exists a t in the closed interval 0 1 such that we can express Z equal to T x plus 1 minus T y. If we can show that norm of Z minus a is less than R, then it will be proved that Z lies in the open sphere SAR. Norm of Z minus a equals with norm of T x plus 1 minus T y minus a. Using triangle inequality, we can write this as lesser equal to t times norm of x minus a plus 1 minus t times norm of y minus a, since both t and 1 minus t are non-negative. Clearly, this is less than R. So, this proves the proposition. Now, we are going to define directional derivative. Later, we shall find that for the same mathematical quantity, we will be forced to change the name from directional derivative to vector derivative. We shall study different notions of derivatives of a scalar field and their interrelation. Later, we shall inquire for their suitability for being a good candidate so that their existence at a point can be used for definition of differentiability of that scalar field at that point. We repeat that any vector has two characteristics, direction and magnitude. First, we give the definition of directional derivative of a scalar field. Let A be a subset of Rn, A be an interior point of the set A, and F is a scalar field defined on the set A. Since A is an interior point of the set A, we can always find an open sphere SAR which lies entirely within the set A. The directional derivative of f with respect to the vector y at the point A is denoted by the symbols dyfa or f dash ay and defined to be the quantity limit of f of a plus hy minus f a by h as h approaches 0, provided the limit exists. Now, f is a scalar field. As h approaches 0, we consider h very close to 0. So, we can assume both a plus hy and a are in the domain of f. Thus, f of a plus hy and f a both are reals. So, their difference is also. So, we are considering limit of a real number f of a plus hy minus f a by h as h approaches 0. If the limit exists, definitely f dash ay is well defined. We start with an example. In this example, we shall find the directional derivative of a scalar field at a point with the help of the definition. Let f be a scalar field defined on Rn by f x equal to norm x square for each x in Rn. We know for every x in Rn, norm x gives us the distance of the vector x from the origin, that is the length of the vector x. Now, we select any a y in Rn where y is different from the 0 vector. We consider the limit of the quantity f of a plus hy minus f a by h as h approaches 0, provided the limit exists. We put the values of f. We know for any vector x, norm x square equals with inner product x x. We also know that inner product is additive as well as homogeneous. So, the quotient f of a plus hy minus f a by h comes to be twice inner product a hy plus mod h square norm y square divided by h. We consider its limit as h approaches 0. So, we find f dash a y or dy f a equals with twice inner product a y. Now, in the definition of the directional derivative f dash a y, let us replace y by 2 y and watch what happens due to this change. As y is different from the 0 vector, y and 2 y are vectors in the same direction, but their magnitudes are distinct. So, we are going to calculate f dash a 2 y. So, this will be limit of a plus 2 h y minus f a by h as h approaches 0. So, we replace 2 h by h dash. So, then we find that the value of the limit is twice f dash a y. In fact, instead of 2 y, if we started with c y where c is any real number, then we can find f dash a c y equal to c times f dash a y, that is d c y f a equals with c times d y f a. Whenever we started the definition of directional derivative, we took y as non-zero. Now, let us relax the condition y non-zero. If we put y equal to 0 vector, then we find f dash a theta equals 0, and this is also compatible with the above result if we put c equal to 0. This clearly indicates that the derivative f dash a y depends on both the magnitude and the direction of the vector concerned, that is y. So, we prefer the term vector derivative instead of directional derivative to use in the following. From the relation f dash a c y equal to c f dash a y, we understood that f dash is homogeneous with respect to its second entry. Now onwards, we shall use the term vector derivative for what we have still told directional derivative. Now, let A be a subset of Rn, A is an interior point of the set A, and F is a scalar field defined on the set A. We define a function g from minus epsilon to r by gt equal to f of a plus t y. Since A is an interior point of the set A, we can always find an open sphere S A epsilon in A. Thus, the existence of such epsilon is assured. Now, we try to find g dash t. So, g dash t equal to limit of g of t plus h minus g t by h as h approaches 0. So, this equals with f of a plus t y plus h y minus f of t y minus f of a plus t y by h as h approaches 0. Writing b equal to a plus t y, we find g dash t equals with limit of f of b plus h y minus f b by h as h approaches 0. This is nothing but f dash b y, that is f dash a plus t y y. In particular, if we put t equal to 0, we find that g dash 0 equals with f dash a y. We shall use this result later. It will be helpful in calculating vector derivatives of scalar fields. We now cite an example. Let f be a scalar field defined on Rn by f x equals with norm x to the power 4 for each x in Rn. Then for any a y in Rn, we have f dash a y equals limit of a plus h y minus f a by h as h approaches 0, provided the limit exists. We put the values of f of a plus h y and f a, and then we simplify it. We can find that we can divide the ratio in two parts for each of which the limit exists. After calculating, we find that f dash a y equals with 4 times norm a square inner product a y. In calculating the second limit, we took the help of our previous example. We do it in an alternative fashion. If we define g t equal to f of a plus t y, then g t is norm of a plus t y to the power 4. By simplification, we find that g t is square of the quantity norm a square plus 2 t inner product a y plus t square norm y square. So, we can find what is g dash t. Putting t equal to 0, we find g dash 0, which happens to be f dash a y, and we have the same value 4 norm a square inner product a y. The advantage of using this method is that we can use the results from single variable calculus, as g was a real valued function of a single real variable. In this particular example, we used chain rule while finding g dash t. We still do not know whether some alike results are valid for vector derivatives or not. Now, we are going to discuss a particular case. Let f be a linear transformation defined on Rn. We have to be careful whenever we are saying linear transformation, its domain is always have to be a linear space. Now, we select any ay in Rn. We are trying to find f dash ay. So, this is limit of f of a plus hy minus f a by h as h approaches 0, as we have seen earlier. Using the linearity property of A, we can find the ratio simplifies to Fy, which is independent of H. So, f dash Ay equals Fy. The above result is also true if f is restriction of a linear transformation on its domain. We cite an example where we can use this result. Let f be a scalar field defined on Rn by f x equal to inner product b x for each x in Rn, where b is a fixed vector in Rn. We now select any x y in Rn and any real number lambda. So, f of x plus y equals with inner product b x plus y. Now, using additive property of inner product, we find that it is nothing but f x plus f y, and f of lambda x equals with inner product b lambda x. Using homogeneity, we find that it is lambda times f x. So, f is a linear transformation defined on Rn. Then for any c and z in Rn, we can write f dash c z equals with f z, and it is nothing but inner product b z. We started defining directional derivatives and then change the name of it to vector derivatives. Now, we are going to give a fresh definition for directional derivatives. Then we shall find the relation between vector derivatives, directional derivatives and partial derivatives. The problem with directional derivatives, the first definition was that we found it changed with the change in magnitude of the vector. However, if we consider unit vectors only, then their magnitude is always fixed, that is 1, and all of them can be easily characterized by knowing their direction only. We give a new definition for directional derivative. Let A be a subset of Rn, A is an interior point of the set A, and f is a scalar field defined on the set A. If y is a unit vector, then the vector derivative f dash a y is called the directional derivative of f at the point A along the direction of the vector y. In such a case, the distance between the points A and A plus hy is mod h. So, the ratio f of A plus hy minus f a by h gives the average rate of change of f per unit distance along the line segment joining the points A and A plus hy. Now, we shall consider a special and interesting case. Let for any I selected from 1 to up to n, E I denotes the ith unit coordinate vector in Rn, that is, which have ith component 1 and all other components 0. Let A be a subset of Rn. A is an interior point of the set A, whose components are A1, A2 up to An, and f is a scalar field defined on the set A. We are trying to calculate f dash A E I. So, it is limit of the quantity f of A plus h E I minus f a by h as h approaches 0. Now, what is A plus h E I? It is A1, A2 up to An plus h times the vector which have ith component 1, all other 0. So, the ratio happens to be f at the point A1, A2 up to An, where the ith component change to Ai plus h, all others remain unaltered, minus f of A1, A2 up to An, and the entire quantity divided by h. We consider its limit as h tends to 0, but we know this is nothing but del f del xi at the point A. This derivative f dash a e I is called the vector derivative of f at the point A with respect to e I, or the directional derivative of f at the point A in the ith direction e I, or the ith partial derivative of f at the point A. We shall also use the symbol DIFA for f dash a e I, that is del f del xi at the point A. Let us now check what vector derivative means when we restrict ourselves to scalar fields defined on subsets of R, that is, when we consider single variable calculus. Let A be a subset of R, A is an interior point of the set A, and f is a real valued function defined on A. We select h and v from R, then limit of f of a plus h v minus f a by h, it is nothing but f dash a v. This happens to be v times f dash a, since h and v are independent to each other, provided the limit exists. That is, in this case we find f dash a v equal to v times f dash a. We recall that the singleton set consisting 1 constitutes the standard basis for the linear space R. Putting v equal to 1, we find f dash a 1, the vector derivative, equals with f dash a, that is the ordinary derivative of f at the point A. Later we shall use this result. In an earlier module, we studied partial derivatives. We found that from partial derivatives of a scalar field, we can constitute higher order partial derivatives. In this module, we define vector derivatives, and we shall show that in a like manner, we can define higher order vector derivatives. For the sake of simplicity, we shall restrict ourselves on scalar fields defined on R2. We start vector derivatives of higher order. Let A be an open set in R2 and f is a scalar field defined on the set A. We select some vector u in R2. Let the components of u be u1, u2. We try to find duf xy, that is f dash xy u1, u2. So, it is limit of the ratio f of x plus h u1 y plus h u2 minus f x y by h as h approaches 0. If this exists for all x y in A, then du f is another scalar field defined on the same set A. Let us denote G equal to du f. So, G is a scalar field defined on the set A. Now, we consider the function du g x y, that is g dash x y u1 u2. By definition, it is limit of the quantity g of x plus h u1 y plus h u2 minus g x y by h as h approaches 0, provided the limit exists. In case du g is well defined for each x y in A, we get another scalar field defined on the same set A. We denote this by the symbol du g. So, that is du operating on du f, that is du f. This scalar field is called the second order vector derivative of f with respect to the vector u. Now, let us consider some vector v in R2 whose components are v1, v2. We can also consider the function dvg xy, that is g dash xy v1, v2, which is defined by the limit of the quantity g of x plus hv1 y plus hv2 minus gxy by h as h approaches 0, provided the limit exists. In case dvg exists for each xy in A, we get another scalar valued function defined on the same set A. We denote this by dvg, that is dv operating on duf, that is dv duf. Similarly, we can also define du dvf. If u and v are distinct, such scalar fields are called the second order mixed vector derivative of f. We recall that for any scalar field f, d10f equal to del f del x and d01f equal to del f del y. We have already studied the Schwarz example, in which we found that del 2f del x del y was different from del 2f del y del x. Keeping that in mind, we can assert that in general du dvf is different from dv duf. So, in this module we defined vector derivatives. We studied some examples where we have seen how to calculate vector derivatives of scalar fields. We studied higher order vector derivatives. In the next module, we shall study properties of vector derivatives.